All right, now we're going to move on to a different concept, velocity, which is lesson 5. And it is important to state that many people confuse speed with velocity. It's like, well, what the heck is the difference and why are we learning about the two of these? But once you learn about the background, you understand that there's quite a big difference between speed and velocity. It comes down to, well, if I look at the learning objectives, we are going to learn about velocity, but it really comes down to something called vectors and scalars. And that's going to help us understand the difference between speed and velocity. Finally, we'll look at some more graphing methods that are related to velocity. The graphing methods are very, very similar to those graphs used for speed. So you're going to really want to make sure as we go through this, you're going to want to understand the connection there with slope. Okay, and we're going to come to some examples again, but you really need to ensure you understand how to calculate slope and how it actually relates to different variables and allows us to determine a value. All right, let's move on. Speed versus velocity. Now, people have always said to me, they go, whoa, why the heck do I have two formulas that are virtually the same, and how would I ever know which one to use? Let's look at speed. Speed is what we did in the last lesson. Speed is the rate of motion of an object. Direction is not included. Now, if you look at specifically, the formula is v equals d over t, but we have to consider what d is. In this case, d is distance. T is time. So imagine, I've always kind of figured this, if you've run around go around a high school running track, typically they are 400 meters in length. Let's pretend the start line is right there. That's the start. If you ran around this track once, obviously your distance would be 400 meters. And let's pretend the time, I'm just making this up, I have no idea what a good time would be. Let's say you did this in, we'll say 80 seconds. Well, we can work it out from there. If you want me to go a step further, you could see basically that while our distance final was 400 meters, take away our distance initial. Well, how far were you at the very beginning? You had gone nothing. Divided by our time final, we said was 80 seconds. What time did you start at? Well, 0 seconds. And you can see from there, you're going to have 40 divided by 80, and so on and so forth. My point to you here is that we're looking at distance. It simply is, how far have we gone? How far have we moved? And in this case, you will get 80 meters per second. So now it's like, well, what the heck? What's different here? Because the formula looks just about the same for velocity. Velocity describes both the rate of motion and direction. So when you have velocity, you're going to have a quantity or a magnitude and a direction. Now, I want you to notice that the D is different. It's displacement. And we'll talk about that in a moment. Another difference you're going to see is there is this symbol. Now, that officially is a little bit of an arrow. And that means that's supposed to be, by putting that on top of the V, it means we're talking about velocity. Okay. There's a few things going on here. Now, what I'm going to do is I'm just going to kind of give us some space for we can kind of talk about this a little bit more, because I want us to really focus on what velocity is and how it's different. So if we use our example here of the track, you're going to go around it, and we know it's a 400-meter track and all of those good things. But the key word here, everyone, is displacement. And what the heck does displacement mean? Displacement is basically how far from where you started. So if you look at this equation right here, you start right here. It's a 400-meter track. You go all the way around. You come back, you do your one lap, and you're done. Now our distance is 400. Your body has physically moved 400 meters. But what's your displacement? How far are you from where you started? Well, in this case, you actually get 0 meters because you're right back to where you started. Your displacement is 0. And then we'd have our time. Now, we'll get into some examples with that. One last thing. Let's just pretend that we had a displacement. I'm just going to make this up, getting away from the track example for a second. It's especially important to know the difference here in our final answer. Let's just pretend we had our displacement was 5 meters. We'll say it's in the east direction in 2 seconds. When you answer this, I put a V with that little weird arrow on it. Okay, now so how would you find this? You would have to do your division, and you would get an answer of 2.5 meters per second. Then you must also give your direction, which is east. All right? So I'm trying to show you here that when you have velocity, the things that are different are you have a little vector arrow on top of the V. The D now stands for displacement, and displacement is how far are you from where you started. Next, in your final answer, you actually have two things now. You have a value of 2.5 meters per second, and you also have a direction. We'll play around with this some more. Now, these are some tables here, or two tables, and I wanted to show you what the difference is between a scalar and a vector. Now, a scalar is something that has a magnitude or a quantity, but it does not have a direction. Length, area, volume, speed, mass, density, temperature, pressure. You see, for example, if I said to you, if we were driving in a car and I said, how fast are you driving? And you said, I'm going 60 kilometers per hour. 60 kilometers per hour, that is a speed. It's a speed because you have not included a direction. On the other hand, if I said to you, how fast are you going and in what direction? If you said 60 kilometers per hour and we were going south, that now is a vector because it has a magnitude and a direction. Now you need to really, really think about those things, okay? These are simply quantities or magnitudes, but no directions. A vector quantity, it has a magnitude and it also has a direction, okay? It's really important to keep that in mind, and that's going to help you understand the difference as we move along here. To be honest, I would very much ensure that you know the difference here. You want to know the difference between a vector and a scalar, and it's going to also influence calculations, and you will see this. All right, so one quick review here. Again, I just think it's so important that we talk about distance one more time. Distance is a scalar because it does not have a direction. It has no direction. And it simply is, it's how far have you moved from a reference point. So if you look, this is our reference point. And we have moved, in this case, this is where we started. We have moved 10, let's say 10 meters. So quite simply, our distance is 10 meters. You might see sometimes they're going to use this open triangle with a D. This right here means change, and you'll see that in things like chemistry and physics. In this case, how much has our distance changed? It has moved 10 meters. Very, very simple and straightforward. But now let's look at displacement. Now, in this, nothing much has changed here, except for displacement is a vector quantity. So if you look at this, the person still has started, this is your reference point, and the person has moved 10 meters to the right. Now, what I want you to say here is you can no longer just say 10 meters. You must somehow reference the direction. You could go 10 meters to the right. Okay. Sometimes you'll see something like this. It'll just be change in D equals 10 meters. Quite often, now you see, whether it's stated or not, sometimes you'll see the plus sign, sometimes you won't, but here's my point. When you move in the positive direction, that's the right-hand side. You see, let's pretend it was like this. If you had a change in displacement of minus 10 meters, that would communicate a move to the left. That would be in this way. Because remember, when your x-axis, this way is positive, 1, 2, 3, 4. And on the other way, it'd be -1, -2, -3, and so on. So you could say 10 meters to the right, or it could be positive 10 meters. There's a whole bunch of ways this happens. The whole point with displacement is you must have a quantity and you must have a direction. Now here's where it kind of gets a little bit interesting in terms of calculations, and you'll see why you would get different answers. In this question, the person has started at the reference point, which is right in the middle. It's that sign again. And what they've done is they've moved 3 meters to the right, and then from there they moved 5 meters to the left. Now, you'll see the huge difference here. For distance, which is a scalar, we simply just want to know how far has your body moved. In this case, the person moved 3 meters to the right, then they moved 5 meters the other direction. That's a total of 8 meters of travel. That's it. The difficult one, though, is displacement. Displacement. How far from where you started. So if you look at this question, you start in the middle. That's the reference point. The person went 3 meters this way. From there, the person turned around and went 5 meters the other direction. Well, how far are you from where you started? And if you look, so the person was 3 that way. Now, it took 3 to there, and the person went 2 more, because 3 and 2 is 5. So what is our displacement? It should be -2 meters, or you could say 2 meters left. That's a very different answer. Our distance is 8, because that's how much has been traveled. But our displacement, or how far you are from the start, is actually 2 meters to the left. I hope you understand the difference here between distance and displacement. This is a very crucial piece of information. Okay, so what I did here is I just wanted to give you a very basic look at the formula. So velocity is displacement divided by time. We've looked at that. Again, I want you to notice that it has that weird arrow. Now, I think the textbook probably draws it a lot better, nicer than I do. It's kind of perfect like this. I was always taught just to kind of do this weird half arrow. Doesn't really matter. Anyway, remember, this is your change, your displacement. This is your change in time. Here's your formula. You have displacement final minus displacement initial, time final. Nothing's really changed. Remember, when you do velocity, at the very end, you're going to put a V with that arrow on top. And then you must have a magnitude and a direction. As an example, you have a person walks 10 meters east away from a bus stop in 5 seconds. What is the average velocity? The calculation is very, very simple. Please remember, you must put V with that little vector symbol on top, and you'll see that I have my 2 meters per second, and I have my direction. It's extremely important. That's what a calculation looks like from start to finish. You have your blank formula, you input your values with units, and then you have a final answer. It's really important. People often ask, do I need to show my work? Well, whether it's chemistry, physics, so on, it doesn't matter. Showing your work is vitally important. Long story short, this is something that you're going to do between now and the day you graduate and going further into school. You must show your work from start to finish. Here I wanted to show you again, you will recall when we looked at speed, we could relate speed and time. And when we related, distance and time. In the last lesson, what we did is we had, this was distance, and this was time, and we had our straight line, and we could figure out the slope, and our slope allowed us to calculate the speed because we related distance and time. Well, very much the same for velocity, just one thing has changed, and that's right here. It is now our position or our displacement. Again, I'm going to show you the calculation one more time. I'm going to take this point and this point. I'll call this point A, this is point B. And just so you know, you could take other points on here. I could have taken these 2 points. It doesn't matter. It doesn't matter which order you put them in. I could have made, I'll even show you. I'll make this one A and I'll make this one B. It does not matter at all. Here's so A, the ordered pair for A would be 2, 10, and for B it would be 8, 40. So now if I use my formula, I'll make this, we'll go x1, y1, x2, y2. Those could be switched. These could have been the 2s and these could have been the 1s. It doesn't matter. Okay, so y2 is 40 meters minus 10 meters divided by, now I'm on x2, should be 8 seconds minus 2 seconds. You'll notice I have units everywhere. This is 30 meters. This is 6 seconds. So, again, now I just, simple calculation, that's 5 meters per second. You can put the 1 there or not, doesn't matter. And what's the one thing I'm missing now? This is velocity, which is a vector, so I better say what direction we're going, and I believe we are going to the east. So your velocity with that arrow is 5 meters per second to the east. Again, everyone, you can see here what we've done is we've taken our position, our displacement, we have related it to time. And by relating those two variables together, those two values, we can calculate our velocity. I hope that this whole concept of slope is becoming a little more clear for you. Just like before, I want to show you this. It makes sense. If you look at this table, the velocity has remained the same over time. 0 seconds, 2, 4, whatever. So if we were to compare velocity versus time, the velocity stays the same. That gives you a straight line horizontal graph. If you wanted to calculate the slope, you could, and you would get, it has 0 rise over a run. Now, end of the day, that would calculate out to 0 meters per second squared, which is an acceleration value, which we haven't learned about yet. But long story short, we have 0 acceleration, which means the velocity is not changing. And I think that makes sense. So again, when you compare, if you have constant velocity and you compare that to time, you will get a straight line graph. And that actually, we saw that when we had a constant speed in the last lesson. So in some ways, speed and velocity are very similar, except for one major difference, and that is the displacement. So there we go. It's very important. One last thing, I've shown you the main methods here of graphing. I would like you to learn on your own about the x-axis method on graphing. Page 139, look at the example. You're also going to learn about the navigator method on page 140. Look at the example. Now, I'm not just saying this like I expect you to know this, and I do expect you to read this on your own and gain the information. I would watch this presentation again. I would certainly read 137 to 144. It's a crucial part of this physics unit. There are going to be questions related to this. I really, really hope that you know the difference between speed and velocity. And I hope you know how vectors and scalars play a role. For example, distance versus displacement. There's a big difference there. So again, you have speed versus velocity, but it's all about the scalars and vectors. Please watch this again. Please try the practice questions. It is crucial that you have this information cemented before we move on.